Every wireless signal you rely on, whether you're streaming a 4K movie on your couch or just swiping through social media at a coffee shop, it actually spends about 99% of its journey trapped inside a physical underground wire.
Yeah. It really is the ultimate illusion of modern computing.
Right. It's a total paradox. I mean, we talk constantly about the cloud or, wireless connectivity, completely ignoring the fact that our invisible digital lives are chained to this massive physical, heavily engineered global machine.
Exactly. I mean, the moment your wireless signal hits a router, it's immediately converted into electrical pulses or flashes of light.
Wow.
And from there, it's hurled through this absolute labyrinth of copper, plastic, and glass that spans oceans and continents. If you actually look at the blueprints of the internet, it looks, well, less like a cloud and much more like a massive plumbing system.
Which brings us to today's mission. We've pulled a massive stack of comprehensive IT certification training materials. These are like the exact manuals and technical specs used to train network engineers on how to build and maintain this hidden infrastructure.
You're incredibly detailed, yeah.
So, whether you're staring at that chaotic drawer of doom in your kitchen, the one,
Yeah.
full of mysterious tangled chargers, or you just want to understand the physical reality of the hardware running your life, we're going to decode the blueprints in this deep dive.
It's going to be fun.
Okay, let's unpack this. Because before a signal ever reaches a laptop or a server, it has to travel the raw highway. And the most common highway in the world is the stuff buried inside our walls and ceilings. We usually just call it an Ethernet cable.
Right, and if you were to actually cut open that standard Ethernet cable, you'd quickly realize just how much engineering is hidden under that simple outer plastic jacket.
It's not just one wire in there.
Yeah. No, not at all. You wouldn't find just one thick wire. You would find 8 very thin, individual, color-coded copper wires. But the crucial detail is how they're arranged.
Right.
They're grouped into 4 distinct pairs. You have a blue pair, an orange pair, a green pair, and a brown pair. And within each of those pairs, the 2 individual wires are tightly twisted around each other.
Okay, so this is known as unshielded twisted pair, or UTP.
Exactly.
UTP. So I have to admit, when I first started looking through the engineering diagrams, I just assumed the twists were a manufacturing convenience.
Mm-hmm.
Like just a way to keep the inside of the cable organized and physically flexible.
That's what most people think.
But looking at the physics involved, those twists are actually a highly sophisticated defense mechanism against the environment.
They absolutely are. It solves really one of the oldest problems in electrical engineering, which is electromagnetic interference, or EMI.
Which is everywhere, right?
Oh, yeah. Our modern world is incredibly noisy on an electrical level. Fluorescent overhead lights, elevator motors, microwave ovens, even just other cables nearby, they all throw off invisible electromagnetic fields.
Right, okay.
So when you try to send a delicate, low-voltage data signal down a long piece of raw copper, those outside fields literally crash into the wire and distort the data. And if the distortion is bad enough, the receiving computer just gets pure garbage.
Okay, so how does simply twisting the wire stop a magnetic field from corrupting the data?
Yeah.
Because the interference is still hitting the copper, right?
It is, yeah, but the defense relies on something called differential signaling.
Okay.
So when a piece of network gear sends a signal, it doesn't just send it down one wire, it sends the positive data signal down the first wire of the pair, and it simultaneously sends an exact inverted negative mirror of that signal down the second wire.
Oh, interesting.
Right. And because the 2 wires are constantly twisting around each other, they occupy the exact same physical space in the environment. This means any electrical noise from the outside hits both wires equally.
Oh, I see the mechanism now. The interference adds a random spike of energy to both the positive wire and the negative wire at the exact same moment.
Right. And when those 2 signals arrive at the receiving computer, the hardware does a quick mathematical trick. It takes that negative mirror signal and flips it back to positive.
Okay.
When it does that, the random spike of interference on that wire also gets flipped, becoming a negative spike. The computer then combines the 2 wires, so the positive noise from the first wire perfectly cancels out the negative noise from the second wire, leaving nothing behind but pristine data.
That is just brilliant. It is essentially the exact same acoustic trick used in noise-canceling headphones.
Yes, exactly.
But it's achieved entirely through raw copper geometry and voltage inversion instead of software.
Which is wild to think about.
But looking closer at the physical specs, there's another layer to this puzzle. The 4 different color-coded pairs inside the cable, they aren't twisted identically. The green pair might have a very tight twist, while the brown pair right next to it has a much looser, longer twist. Why vary the rate of the twist?
Because environmental noise isn't the only threat, the wires also threaten each other.
Oh, from within the cable itself.
Right. Whenever electricity flows through a wire, it creates a small magnetic field. If you have 4 pairs of wires crammed tightly together inside a tiny plastic tube, the signal from the blue pair can actually bleed over and corrupt the green pair. This is called crosstalk.
Got it.
So if every pair had the exact same twist rate, their physical peaks and valleys would line up perfectly, creating a highly efficient bridge for that crosstalk to travel across.
So by varying the twist rate, you prevent the pairs from physically synchronizing. You break the bridge.
Precisely. It scrambles the physical alignment just enough that the crosstalk can't effectively couple between the pairs. It is an incredibly elegant mathematical solution applied to raw metal.
And this raw metal geometry is ultimately what dictates the speed of the network. Though, a really interesting distinction in the IT materials is that a cable itself doesn't inherently have a speed.
Right.
It's just passive copper. The speed actually comes from the signaling standard that the network switches try to push over the wire.
Yeah, that standard is managed by the Institute of Electrical and Electronics Engineers, the IEE. They define what frequency and signaling method the hardware uses. But you can't just push a massive high-frequency signal over any cheap piece of copper.
Because it would just bleed everywhere.
Exactly. The
Yeah.
higher the frequency, the worse the crosstalk and the signal degradation become. So the IEE dictates the minimum physical category of cable required to support a given standard.
Which brings us to the famous categories. For a long time, the baseline for a standard home or office network was gigabit speed, which requires Category 5e cable. The E stands for enhanced.
Yep. Yeah.
And the physics of Cat 5e allow that gigabit signal to travel a full 100 meters before it degrades too much. But if a company wants to push 10 times that amount of data, like a 10 gigabit signal, the older copper just physically cannot contain the crosstalk at those higher frequencies.
No, it just falls apart. So you have to step up to Category 6. Cat 6 utilizes tighter twists and often includes a physical plastic separator running down the middle of the cable to keep the 4 pairs physically isolated from each other.
Oh, wow.
But even with that, physics starts to win out. An unshielded Cat 6 cable can only carry a 10 gigabit signal for about 55 meters before the data falls apart. To push 10 gigabit, the full 100-meter distance, network architects have to upgrade to Category 6A.
Where the A stands for augmented.
Right. It has even stricter twist tolerances and thicker insulation.
You bring up shielding, which is a whole other dimension. We started with UTP unshielded twisted pair, but the engineering specs detail an entire matrix of shielded twisted pair, or STP, options. You see designations like SFTP or FUTP printed right on the sides of the cables.
The naming convention is highly specific. The letter before the slash tells you the shielding for the entire outer cable, and the letter after the slash tells you the shielding for the individual twisted pairs inside. U stands for unshielded, S stands for a braided metal screen, and F stands for a foil shield.
So, like, reading that like a map, an FUTP cable would have an outer foil shield wrapping the whole bundle, but the twisted pairs inside remain unshielded.
You got it.
Whereas an SFTP cable is essentially locked down a heavy braided metal shield around the outside, an individual foil wrapping around every single twisted pair inside.
Which is exactly what you need in highly industrialized environments. If you're running a network line across a factory floor right next to, say, a massive robotic welding arm, the standard twist geometry just isn't going to be enough to stop that level of magnetic interference. You need the physical metal shielding to deflect the noise.
That makes total sense for heavy machinery indoors. But what happens when you need to run a copper cable outside, say connecting a security camera on the far edge of a campus? You obviously can't just bury a standard indoor cable in the dirt.
Oh, definitely not. For that, you deploy direct burial cables. These are heavily modified for survival. They incorporate a dedicated drain wire running the length of the cable to provide a continuous electrical ground against lightning strikes or massive power surges.
That's intense.
And more fascinatingly, the hollow spaces inside the outer jacket are often completely filled with a specialized waterproof gel.
Wow, gel.
Yeah, this prevents water from seeping into the cable and destroying the electrical characteristics of the copper, allowing them to be buried directly in the earth.
Surviving the elements outdoors makes intuitive sense. But diving into the commercial building codes, there's a fascinating environmental hazard regarding where you place cables indoors, specifically the space above a drop ceiling.
Right, the plenum space.
Yeah. In commercial architecture, the open space between the structural roof and the suspended ceiling tiles is heavily utilized by the HVAC system to pull return air back to the central air conditioner.
Mm.
The manuals are very strict about this. You absolutely cannot run a standard, cheap PVC-coated network cable through a plenum space.
If we connect this to the bigger picture, this is purely a life safety mandate. A standard polyvinyl chloride or PVC jacket is highly combustible.
Right.
And worse, when it burns, it releases thick, highly toxic black smoke. If a fire breaks out in a plenum space filled with cheap PVC cables, the HVAC system will instantly suck up that toxic smoke and forcefully distribute it through the air vents into every single room in the building.
So using non-plenum cable in a ceiling is basically like installing flammable, toxic air fresheners directly into the building's mechanical lungs.
That is exactly what it is. Building codes require plenum-rated cables for these specific areas. These jackets are made from specialized plastics, like fluorinated ethylene polymer, or FEP, or a chemically modified low-smoke PVC. They are more expensive, they're physically stiffer, and honestly, network installers generally dislike working with them.
But they won't kill you.
Right, they will not actively poison the occupants of a building during a fire emergency.
So we have our physical copper highway. It survives the elements, it deflects interference, and it meets fire codes. But raw wire doesn't accomplish anything until it's correctly terminated so a device can actually send a signal. We need a universal physical handshake, which introduces the connectors themselves.
Right. In the networking world, these are the modular connectors. The two most ubiquitous are the RJ11 and the RJ45.
Oh man, anyone who has ever tried to troubleshoot their home internet router in a dark room knows the physical frustration of these two.
Oh, absolutely.
Because the RJ11 is the smaller of the two. It usually houses just two tiny metal contacts, and it was designed primarily for analog telephones and older DSL internet lines.
Yep.
The RJ45 is the larger connector. It houses all 8 of our twisted copper wires, and it's the global standard for Ethernet. The sheer frustration comes from the fact that because the RJ11 is smaller, you can accidentally jam a telephone cable perfectly into a larger RJ45 Ethernet port, and it will just sit there, wedged in, doing absolutely nothing.
It is a design flaw that has plagued IT help desks for decades. But the bigger challenge with the RJ45 isn't the shape, it's the internal mapping.
Right.
You have a plastic connector, and you have 8 tiny, unspooled colored wires. You need a universal agreement on exactly which color goes into which tiny slot. Otherwise, a computer in Tokyo would have a completely different pinout than a server in New York, and the electrical pulses would hit the wrong receivers.
And reading through the international standards, this is governed by the Telecommunications Industry Association. They established 2 acceptable maps for wiring an RJ45 connector, T568A and T568B.
Yeah, the existence of 2 standards is mostly a quirk of telecom history, but they essentially achieve the same goal. They assign the orange, green, blue, and brown pairs to highly specific pins. In the U.S. commercial sector, T568B is generally the default standard. The crucial rule, however, is consistency across a single cable.
Oh, you can't mix them.
Exactly. You cannot wire one end of a cable using the T568A map and the other end using the T568B map and expect a modern gigabit connection to work properly.
Because the mapping differences fundamentally swap where the green and orange pairs land physically inside the connector.
Yeah.
Right?
Yes.
So if you mismatch the ends on a modern network, a computer pushes its high-speed transmit signal down the wire, and instead of hitting the receive pins on the router, it crashes directly into the router's transmit pins. You get data collision and a dead link.
Right.
Now, manually crimping 8 tiny wires into a plastic connector makes sense for a single cable at a desk. But if you're an architect wiring a skyscraper with 10,000 individual wall ports, nobody is sitting in a server room manually clipping 10,000 tiny plastic RJ45s.
Ooh, no. That scales terribly. For commercial infrastructure, engineers use punch-down blocks.
Okay.
Imagine massive arrays of plastic teeth mounted onto server room racks. Instead of crimping a connector onto the wire, an installer strips back the thick outer jacket, lays the 8 individual colored wires across the corresponding teeth on the block, and uses a spring-loaded punch-down tool to physically force the wire down into a slot.
And the mechanism inside that slot is brilliant. It uses insulation displacement contacts.
Yep, IDCs.
There is a tiny V-shaped metal blade hidden inside the plastic block. When you punch the wire down, that metal blade physically slices through the colored plastic insulation of the individual wire and bites directly into the copper core. You don't have to strip the tiny wires at all.
Not at all.
The block does the cutting and the connecting. in a single violent push. It allows a technician to terminate hundreds of connections in a fraction of the time.
It is highly efficient. And before we completely leave the realm of copper, it's worth acknowledging coaxial cable, specifically the F connector.
Oh, right.
This is the threaded metal barrel with a single, thick, solid copper needle in the dead center. This is the cable you have to physically screw onto the back of a broadband modem.
And unlike the twisted pairs, which use differential geometry to fight noise, coax relies on brute force physical shielding.
Yeah, totally different approach.
That center copper wire is surrounded by a thick white plastic dielectric insulator, which is then wrapped in a heavy braided metal shield. It allows internet service providers to push massive amounts of data over miles of outdoor cable using the ics broadband standard, all while keeping the signal completely isolated from outside radio interference.
Coaxial and twisted pair are marvels of electrical engineering, but they both share a fatal limitation.
Right.
They rely on electricity. No matter how tightly you twist the copper or how much metal shielding you wrap it in, eventually the resistance of the metal and the degradation of the signal win out. You simply cannot push an electrical network signal between two cities. To conquer distance, we have to abandon electricity entirely. We transition to light, we move to fiber optics.
And this completely changes the physics of the physical layer. A fiber optic cable doesn't care about electromagnetic interference because a laser beam is completely immune to electrical noise.
Exactly.
But the anatomy required to guide light over miles of physical terrain is incredibly delicate. At the center is the core, a microscopic strand of highly purified glass. Wrapped tightly around that core is a layer of glass called the cladding.
And the relationship between the core and the cladding is the magic of fiber optics. They're engineered to have different refractive indexes.
Okay, what does that mean in practice?
The cladding basically acts as an optical barrier. When a pulse of light travels down the core and tries to bleed out the side, the cladding forces the light to bend back inward. This is called total internal reflection. The light is essentially trapped, bouncing continuously down the core until it reaches the other end.
Then you add a protective buffer coating to stop the glass from snapping, and terminate it inside a tiny ceramic cylinder called a ferrule to keep the microscopic core perfectly aligned with the laser on the switch.
Right.
But diving into the fiber types, the industry splits this technology into two distinct camps, based entirely on the distance of the run.
Right. You have multimode fiber and single-mode fiber. Multimode is typically deployed for shorter, high-speed runs. Think of connecting two server racks in the same room, or maybe running a backbone link between two floors of a high-rise building.
And the physics of why it's called multimode is fascinating. Multimode fiber has a relatively wide glass core. Because the core is wide, it can use cheaper, slightly less focused LED light sources instead of pure lasers. The light enters that wide core and bounces wildly off the cladding at many different angles. It takes multiple different paths or multiple modes to reach the destination.
Yeah.
Here's where it gets really interesting. It is essentially like shining a wide beam flashlight down a long mirrored hallway.
I love that. That's a great way to visualize it. But that wide core creates a profound problem over long distances, known as modal dispersion.
Okay.
Because the light is bouncing, taking multiple different paths, some photons travel in a relatively straight line, while others bounce drastically side to side. The straight-line photons arrive at the receiver slightly faster than the bouncing photons.
Right, because they took a shorter path.
Exactly. Over a few hundred meters, it doesn't matter. But if you try to run that multimode signal for 10 kilometers, the light pulses arrive at vastly different times. The signal smears together, and the data is corrupted.
So to cross a city or cross an ocean, you have to eliminate the bouncing. You use single-mode fiber. Single-mode shrinks the glass core down to microscopic proportions so thin that light can only physically travel straight down the center. There's no room to bounce.
None at all.
And to push a signal down a pipe that small, you have to replace the LED with an incredibly precise high-powered laser. To borrow the previous thought, single mode is like firing a sniper's laser perfectly straight down a tiny pipe. One path, one mode, zero smearing over massive distances.
That is perfectly stated. And as this optical technology advanced, the physical connectors had to evolve to meet the sheer density required by modern data centers. Early fiber networks used the ST connector, the straight tip. It used a push-and-twist bayonet lock, somewhat similar to an older security camera connection. It was incredibly secure, but you needed physical space for your fingers to twist the lock.
Which you don't have on a dense server rack.
Right. So the industry moved to the SC connector, the standard connector, which replaced the twisting with a simple push-pull mechanism. You shove it in, it clicks, you pull the housing, it releases.
Got it.
But even that was too bulky as server densities exploded. So engineers miniaturized it again with the LC connector, the Lucent connector. It's half the size of the SC, and it secures itself with a tiny plastic retaining clip on top, operating almost exactly like an optical version of the RJ45 Ethernet plug.
Okay, so we've traversed the long-haul optical lasers, we've explored the copper running through the walls, we finally arrive at the physical edge of the network, we reach the desktop.
The fun part.
Right. This is the hardware that interfaces directly with human beings. And the defining standard of this space, the technology that unified peripheral hardware, is USB.
The universal serial bus. And looking at its history in these IT materials, it really is a story of taming chaos. Before USB, the back of a computer was a nightmare of parallel ports, serial ports, and proprietary keyboard plugs.
Missile spaghetti.
Yes, USB promised a single, unified pipeline, but the physical evolution was a bumpy road. USB 1.1 arrived with a massive breakthrough. It offered 12 megabits per second, which was revolutionary for basic mice and keyboards. Eventually, USB 3.0 pushed that to 5 gigabits, and today, USB 3.2 can push an astonishing 20 gigabits per second.
The speed scaled beautifully, but the physical shapes of the connectors became a nightmare.
They really did.
Engineers designed the flat, rectangular type of plug for the computer side because it was robust.
Yeah.
But they realized that shape was too big for a portable device, so they created the square Type B plug for printers. Then they needed something smaller for digital cameras, leading to Mini B. Then smartphones got incredibly thin, requiring the even smaller Micro B.
Right.
The universal bus spawned a half-dozen entirely different cables, almost all of which suffered from the classic problem you always tried to plug them in upside down on the first try.
Every single time. Which catalyzed the development of what is arguably the most important physical connector of the modern era, USB-C. And the most critical conceptual point here is that USB-C is just a physical shape.
Yes, this is a huge misconception.
It is a highly engineered, reversible connector specification. It is not a data speed. The engineering breakthrough of USB-C was cramming enough microscopic pins onto both sides of the internal connector so that it simply didn't matter which way the user plugged it in. The hardware would digitally negotiate the orientation instantly.
It acts as a blank, ultra-high bandwidth pipeline. Depending on what the connected devices agree upon the millisecond you plug it in, that physical USB-C cable could carry standard USB data. It could act as a dedicated power delivery cable to charge a laptop. Or it could enter alternate modes and carry raw DisplayPort or HDMI video signals. Or, in its most powerful form, it carries Thunderbolt.
Right.
Thunderbolt is a technology protocol that essentially takes the core internal data lanes of a computer's motherboard, the PCI Express lanes, and extends them out over a cable. Early versions of Thunderbolt pushed 20 gigabits, but when Thunderbolt 3 adopted the USB-C physical shape, it doubled the bandwidth to 40 gigabits per second.
That's insane.
And Thunderbolt 4 kept that massive speed but guaranteed support for running dual 4K monitors simultaneously. And it supports daisy chaining. You run one single cable from a laptop to a monitor, a second cable from that monitor to another monitor, and a third cable down to a massive external hard drive. The bandwidth handles all of it simultaneously over a single port. It is the pinnacle of desktop consolidation. But legacy video connections still linger heavily in enterprise environments. IT professionals still routinely encounter VGA, the video graphics array. It's a bulky, blue, analog connector. Because it sends physical voltage waves instead of digital packets, the image quality visibly degrades if the cable runs longer than a few meters. Then you have DVI, which awkwardly tried to bridge the analog and digital divide.
Yeah, DVI was a weird middle ground.
But today, if you aren't using USB-C for video, you're likely using HDMI, which carries unified digital video and audio, or DisplayPort. And DisplayPort is fascinating conceptually. It doesn't send a constant stream of raw pixel data like older cables. It actually packetizes the video data, putting it into tiny data envelopes, very much like how an Ethernet network sends data over a server.
Right.
Plus, DisplayPort connectors often feature tiny physical teeth that actually lock the cable into the port, requiring a button press to release it.
And internal to the computer, bridging the gap to physical storage, the standard remains SATA, the serial attachment. SATA solved a major configuration issue by using a highly distinct L-shaped internal connector. It is physically impossible to plug a SATA drive in backward.
Thank goodness.
Right. It utilizes a strict point-to-point architecture. One cable connects one motherboard port to exactly one hard drive, carrying data over a 7-pin connector, while a separate 15-pin connector handles the power.
Okay, I have a major conceptual pushback here based on
Uh-huh.
everything we've just covered. We've discussed 40 gigabit Thunderbolt connections. We've discussed microscopic lasers crossing oceans over single-mode fiber. The physical layer has evolved to the realm of science fiction. So why in the world do these advanced IT training manuals explicitly state that a modern network engineer should carry around a DB9 serial cable?
Ah, right.
This is a bulky 9-pin connector utilizing the RS-232 standard that was literally invented in 1969. Why hasn't this been eradicated?
What's fascinating here is that it survives because of the absolute worst-case scenario. It's a concept called out-of-band management.
Okay. When an enterprise network is functioning, an engineer can log into a router over the fiber optic network seamlessly from 1,000 miles away. But what happens if the operating system on that router corrupts and completely crashes? The high-speed network dies. The fiber is useless. The entire digital highway is shut down.
The digital front door is locked and the building is burning.
Exactly.
Huh.
The only way to save that multi-million-dollar infrastructure is for a human being to physically walk into the server room, bypass the dead network interfaces, and plug directly into the hardware's dedicated console port. And for decades, the undisputed lowest common denominator standard for that direct hardware backdoor has been the 1969 serial protocol over a DB9 cable.
Oh, wow.
It is slow, it is archaic, but it doesn't rely on the network to function. It's the ultimate disaster recovery lifeline.
Which completely frames this entire deep dive. We've journeyed through an invisible physical relay race. Data is generated on a desktop, channeled through the reversible pins of a USB-C cable, handed off to the mathematically twisted copper pairs inside our walls to cancel out electrical noise. Yep.
It navigates through toxic smoke-resistant plenum spaces, gets punched down into massive server racks via microscopic V-blades, and is finally converted into a pure laser beam bouncing perfectly down a glass core across the globe.
It is a profound testament to global engineering. The next time you untangle a messy cable or you stream a video seamlessly over Wi-Fi, you now understand the immense, strictly governed physical architecture that is actively bending physics to make that wireless illusion possible.
Absolutely. Which leaves us with a fascinating final thought to consider before we wrap up.
Yeah, think about this. Right now, physical cables like Thunderbolt and USB-C are the undisputed champions of delivering massive bandwidth and high wattage power. But wireless transmission protocols are evolving at a staggering rate. What happens to our physical world when wireless technology eventually achieves the exact same 40 gigabit speeds and power delivery as Thunderbolt without needing the physical link? In 30 years, will our grandchildren look at a USB-C cable in the drawer of doom with the exact same archaic reverence that we have for a 1969 serial port today?